Hi, everybody. Last time we talked about the compressibility of soil, and today we continue with the time rate of settlement. Okay, let's begin. Not only a settlement should indicate the amount of anticipated settlement, but also give an indication of the rate at which it will take place. To obtain the theory for time rate of settlement using an element of the soil sample of thickness dz and cross-sectional area dA, which is equal to dx times dy as shown in the figure. The assumptions are as follows. The soil is homogeneous. The soil is fully saturated. The solid particles and water are incompressible. Compression and flow are one-dimensional in a vertical direction. Darcy's law is valid. Coefficient of permeability and the coefficient of volume change stay constant throughout the process. Based on the principle of continuity as shown in the figure, where the inflow rate of water into the bottom phase of the differential element equals the area times velocity. The outflow rate of water from the differential element is increased as a result of vertical consolidation of the element. In this equation, the partial differential term, which is delta V sub z over delta z, represents the increase in flow rate in the z direction owing to consolidation of the element. If we subtract the rate of outflow of water from the rate of inflow of water, we get the volume of voids reduced, or the amount of consolidation per unit of time as given in equation 1. The next step is to include Darcy's law, which is equal to K sub z times I, where K sub z is the coefficient of hydraulic conductivity of soil, I is the hydraulic gradient. V sub z may also be written as K sub z times delta H over delta z, or K sub z over gamma sub W times delta U over delta Z, where U is the excess pore pressure due to increase of stress, which is equal to gamma sub W times H. H is the excess pressure head. Gamma sub W is the unit weight of water. K sub Z is the permeability of soil in Z direction. And V sub Z is the velocity of flow of water in the Z direction. Combining equations 1 and 2, we obtain equation 3 as illustrated. The decrease in the volume of soil in terms of the coefficient of volume change can be expressed as delta V, which is the volume change, is equal to M sub V times delta sigma prime times V. Delta sigma prime is the increase in effective stress, and V is the total volume of soil mass. And therefore, the rate of volume change can be written in terms of the coefficient of volume change as given here. The total stress increment is progressively transmitted to the soil skeleton, increasing effective stress, while the excess pore water pressure lessens. Therefore, the rate of volume change can be written as shown in equation 4. Now, combining equations 3 and 4, we obtain the expressions given here. Now, this expression is the differential equation of consolidation, where C sub V is equal to K sub Z or M sub V times gamma sub W. C sub V is defined as the coefficient of consolidation, suitable unit being squared meter per year. Since K sub Z and M sub V are assumed constant, C sub V is constant during consolidation as well. This assumption is acceptable provided that the stress changes are small enough such that K sub Z and M sub V do not change significantly. The solution of differential equation of consolidation requires a knowledge of the boundary conditions. By defining the initial distribution of excess pore water pressures at the boundaries, we can then obtain solutions for the spatial variation of excess pore water pressure with depth and time. Different distributions of pore water pressures within a soil layer are likely. Two of these are displayed in the figures. The first one represents uniform distribution with depth in a thin clay layer, which is the drainage geometry in an odometer test. And the second one represents triangular distribution with depth in a thick clay layer. If the differential equation of consolidation is solved with the following boundary conditions using Fourier series at time t0, which is immediately after loading, the excess pore pressure is equal to stress increase. After some time, the excess pore pressure will completely dissipate at the boundaries of clay layer, at the top and at the bottom. This solution yields equation 5, where small m is a positive integer from 0 to infinite. Capital M is equal to this expression given here. Delta U sub 0 is the initial excess pore water pressure. T sub V is equal to C sub V times T over h d squared, in which T is the time to reach a certain degree of consolidation. T sub V is the time factor, which is non-dimensional number and related to the degree of consolidation as well as the length of maximum drainage path. It is clear that the consolidation process can only take place when water drainage is allowed. The existence of drainage at the top and or bottom of the clay layer is a key factor that influences the time of consolidation. The type of drainage is defined by the parameter HDR. If there is a clay layer of thickness 2 times HDR, which is sandwiched between two permeable layers, such as sand or gravel, then the drainage path is equal to the half of the thickness of clay layer. On the other hand, if the drainage is available only at the top or bottom of the clay layer, then the drainage path is equal to the thickness of the clay layer. A plot of equation 5 results in the variation of excess pore water pressure with depth at different times. Immediately after the application of external load, theoretically at T0 time, the initial excess pore water pressure is equal to the applied vertical stress throughout the soil layer. As soon as the drainage starts, the initial excess pore water pressure will immediately dissipate at the permeable boundaries, and the maximum excess pore water pressure takes place at the center of the soil layer because the drainage path to the free boundaries is the longest one. As time progresses, the excess pore water pressure will continue to dissipate. Finally, when time approaches infinity, the excess pore water pressure becomes zero, and the vertical effective stress increment becomes equal to the total stress increment. As a result, the consolidation process comes to an end. Since the consolidation is attained by the dissipation of excess pore water pressure, the degree of consolidation, in other words, consolidation ratio at distance z at any time t, can be expressed as shown in equation 7. Now, if we include equation 5 in equation 7, we get this expression given here, where delta U sub z is the excess pore water pressure at time t, and delta U sub 0 is the initial excess pore water pressure. In practical problems, it is the average degree of consolidation over the depth of layer as a whole that is of interest. From equation 7, the average degree of consolidation at any time t can be expressed in the form given in equation 8. The substitution of the expression for excess pore water pressure given in equation 5 into equation 8 brings about equation 9. Now, the relationship between the average degree of consolidation and the time factor can be tabulated based on the types of excess pore water pressure distribution with depth. For instance, Table 1 gives a relationship between the degree of consolidation and the time factor concerning the uniform distribution with depth in a thin clay layer. On the other hand, Table 2 presents a relationship between the degree of consolidation and time factor regarding the triangular distribution with depth in a thick clay layer. The values of the time factor and their corresponding average degrees of consolidation for case 1 may be approximated by the following simple relationships. For the average degree of consolidation between 0 and 60%, the time factor can be obtained using this expression. For the average degree of consolidation greater than 60%, time factor can be approximated using this expression given here. The coefficient of consolidation is an important parameter employed to estimate the time of consolidation. It is obtained from the audiometer tests when changes in the sample height resulted from the application of load are recorded with time. The obtained data can be analyzed using either the log time method or the root time method. Now, let us see what they are. In the log time method, the displacement gauge readings are plotted against the times using semi-logarithmic scale as shown in the figure. The first step is to extend the straight line portions of primary and secondary consolidations to intersect at A. The ordinate of A is represented by d sub 100, which is the deformation at 100% primary consolidation. The second step is to select a time t sub 1 near the head of the initial portion of the curve as illustrated, and then another time t sub 2 such that t sub 2 is equal to 4 times t sub 1. Let the difference between these two time intervals be equal to delta d. Then the third step is to draw a horizontal line through a point D such that the vertical distance is equal to delta D. The ordinate of point D is D sub 0, which means deformation at 0% consolidation. The fourth step is to calculate the ordinate for 50% consolidation as D sub 50. Draw a horizontal line through this point to intersect the curve at E. The abscissa of point E is the time for 50% consolidation. Finally, for 50% average degree of consolidation, the time factor is determined from the related table, which is equal to 0.197. Now, remembering the expression for time factor, and if this expression is rearranged in terms of the coefficient of consolidation we are looking for, then we get this expression as illustrated here. Another method to determine the coefficient of consolidation is called square root of time method. In this method, the displacement gauge readings are plotted against the square root of time as shown in the figure. The first step is to draw the best straight line through the initial part of the curve intersecting ordinate at A and abscissa at B. The second step is to draw a line AC such that OC is equal to 1.15 times OB. The abscissa of point D, which is the intersection of AC and the consolidation curve, gives the square root of time for 90% consolidation. Finally, for 90% consolidation, the corresponding time factor is taken from the related table, and then the time factor expression is rearranged in terms of the coefficient of consolidation as illustrated. What method should we use then? The log time method utilizes the early and later time responses, while the root time method takes advantage of the early time response, which is expected to be a straight line. In theory, the root time method should provide good results, except when non-linearities resulting from secondary compression lead to substantial deviations from the expected straight line. These deviations are most pronounced in fine-grained soils with organic materials. Additionally, several investigators have stated that the coefficient of consolidation value obtained from the field is substantially higher than that obtained from conventional methods. Therefore, one of these methods will be explained here, since it may provide a more realistic value of field work. Early stage log time method is comparatively new one. To determine the coefficient of consolidation from the sample deformation against the log of time, the following constructions are required. In the first step, select times t sub 1 and t sub 2 in the curved portion as shown, such that t sub 2 is equal to 4 times t sub 1. Let the difference of sample deformation between these time intervals be delta d. In the second step, draw a horizontal line DE such that the vertical distance BD equals delta D, and the displacement corresponding to the line DE is equal to D sub 0, which means the deformation at 0% consolidation. In the third step, draw a tangent through point F as shown. The tangent intersects the line DE at point G. And finally, determine the time corresponding to point G, which is the time at 22.14% consolidation. Now, the time factor corresponding to this degree of consolidation is either obtained from the related graphs or from the tabulated values, and the time factor is rearranged accordingly to determine the coefficient of consolidation as given here. Practical example 1. A hospital building with its total load of 270 meganewton is planned to be constructed on a site made up of a 2-meter thick sand layer underlain by a 5-meter thick normally consolidated clay layer, beneath which an impermeable rock layer lies, as illustrated in the figure, and the groundwater table is located 1 meter below the ground surface. The building's raft foundation is rectangular with a width of 30 meters and length of 60 meters. The settlement analysis shows that the clay layer would undergo a significant vertical deformation of about 0.74 meter after the construction of the building. You should remember these examples from my earlier lecture related to the compressibility of soil. It is available on my YouTube channel for those who missed. The laboratory tests carried out on soil samples obtained from the middle of soil layers at site through boring gives the following data presented in Table 1 and in Table 2. The questions are: A. How long will it take for the clay layer to attain 90% consolidation? And B, what would be the consolidation settlement in 3 years? And finally, for the stress range of 50 and 100 kilonewton per square meter, determine the coefficient of permeability of the clay layer. In the solution of this problem, the first step is to determine the coefficient of consolidation using any method explained so far. Here, we adopt the log time method. Initially, settlements are plotted against log of times using semi-logarithmic graph as shown in the figure. Following the procedure for this method explained earlier, T sub 50 is obtained as 6.8 minutes. As this time is related to 50% consolidation, then the corresponding time factor is obtained as 0.197 from the related table. In odometer test, the drainage path is provided on both sides. That's why the drainage path is equal to half of the thickness of soil sample, which is 10 millimeter. Knowing the time for 50% consolidation and the related time factor, the coefficient of consolidation can be calculated as illustrated here. The second step is to estimate the time to attain 90% consolidation. The time factor corresponding to 90% consolidation is taken from the related table, and therefore it is 0.848. Since the drainage in the field will be provided only on the top of alluvial clay layer, the drainage path is equal to the thickness of clay layer, which is 5 meter. The time to achieve 90% consolidation in the clay layer of alluvium will be 14 years as shown. It is obvious that 14 years may not be acceptable for this project, and therefore some other methods related to soil consolidation should be considered. The most popular one being preloading. The third step is to calculate the consolidation settlement in 3 years. Now the time factor for 3 years can be calculated as shown and obtained as 0.183. This corresponds to 48% consolidation. Thus, the settlement after 3 years can be calculated as 0.36 meter. The fourth step is to figure out the coefficient of permeability. For these, we need to determine the void ratios corresponding to 50 kilonewton per square meter and 100 kilonewton per square meter stresses, which are 1.76 and 1.58 respectively. If we place the void ratios and the corresponding stresses in the equation given here, we obtain the coefficient of volume compressibility as 0.0013 square meter per kilonewton. The coefficient of permeability can then be obtained based on the coefficient of consolidation, the coefficient of volume compressibility, and the unit weight of water as illustrated. The coefficient of permeability is equal to 8.9 times 10 to the power of minus 10 meter per second. The question is, does it mean that we can use data from the odometer test instead of the falling head test to obtain the coefficient of permeability of clay soil? The answer is yes. According to the theory, these two methods are expected to give similar results. Practical example 2. You will remember this example from our earlier lecture about the compressibility of soil as well. A detached house underwent a differential settlement of 21 millimeter 2 years after the completion of its construction. It is figured out that the house would undergo a total differential settlement of about 82 millimeter and become risky if the differential settlement exceeded 55 millimeter. Therefore, the owner would like to know how long will it take before the house poses a risk. To solve this problem, the first step is to calculate the degree of consolidation for the present differential settlement of 24 millimeter. Remember that we can also define the degree of consolidation as a ratio between the settlement at any time t and the total settlement. In our example, the present settlement is 24 millimeter and the total settlement is 82 millimeter. So the average degree of consolidation can be obtained as 29.3%. For the degree of consolidation in between 0 to 60% in our case, the equation for the time factor given here should be used. And the time factor is obtained as 0.067. Based on the time factor, drainage path, and the time for settlement, the coefficient of consolidation of clay layer beneath foundations can be estimated, which is 0.134 square meter per year. Notice that the drainage path is 2 meter, which is the thickness of clay layer beneath foundation B. Because the clay layer is underlain by rock layer, which is impermeable. And therefore, there will be one-way drainage from the top of clay layer. That's why the drainage path is equal to the thickness of clay layer beneath foundation B. The second step is to calculate the degree of consolidation for 55 millimeter differential settlement. For 55 millimeter differential settlement, The average degree of consolidation can be calculated as 67.1%. Since it is greater than 60%, the equation to calculate the time factor given here should be used. And the time factor can be obtained as 0.365 accordingly. Now, based on the drainage path, the time factor, and the coefficient of consolidation of clay layer beneath the foundations, the time needed for 55 millimeter differential settlement will be around 11 years. This means that in the next 9 years, the total differential settlement would be 55 millimeter, and it would not be safe to continue living in the house thereafter. It is quiz time now. The first question: the rate of settlement depends on the permeability of soil. True or false? Which one? Yes, the answer is A. The statement is true. The second question: if two layers of the same soil have the same degree of consolidation, then the time factors are what? Be careful. No, it is not. The answer is A. They are equal. The third question is: a 50-meter thick soil can only drain from its top surface. The drainage path length is then very easy. Yes, the answer is A. Well done. Which of the following is the coefficient of consolidation? Easy for you? Yes, the answer is B. The fifth question: a layer of clay whose thickness is 10 meter is expected to have a total settlement of 1 meter. What was the degree of consolidation when the settlement was 10 centimeter? This should be easy for you. It's a very simple calculation. Go on. Which option is the right answer? Yes, the answer is B, 10%. Jolly good. The sixth question: when time factor approaches infinity, the average degree of consolidation becomes unity. True or false? No, the answer is A. What a pity. Which of the following statement is not correct considering the theory of one-dimensional consolidation? Which one? No, the answer is C. Soil is anisotropic. Remember, it is assumed that soil is isotropic. So don't forget this. The eighth question: the log time method to determine the coefficient of consolidation is designed to obtain the time necessary to achieve what? No, it is not. Sorry. The answer is A, 50% consolidation. Remember that the log time method is one of those methods to determine the coefficient of consolidation. And the final question: the average degree of consolidation is conventionally employed to find the time rate of settlement. True or false? Yes, you got it. The answer is A. Congratulations. I think that's all I have to say. Thank you for listening. Hope to see you again. All the best.